Our next speakers are going to be Aranya Chakrabortty of North Carolina State University and Yufeng of UNC Chapel Hill. This is the duo that won the Best Energy app last year, and they're back on something on the similar platform. Their application is called Secure-WAMS. The goal of Secure-WAMS is to leverage low-latency wide area networks to identify in real time malicious attacks of the cyber or physical resources of the power grid, and to reconfigure the routing to bypass an immediate attack. In this way, Secure-WAMS is helping prevent disruption of interconnected critical infrastructures such as the power grid or other kinds of critical infrastructure you can imagine. So, as we set them up. By the way, this area of protection of critical infrastructure is something that we at NSF are quite interested and working towards. In fact, in August, we're going to be running what's called an Ideas Lab exactly in this area. So this is a timely thing for my programmatics aspect as well. Aranya.
Thank you, Keith. Thank you.
Yeah, number 2.
All right. Thank you very much, Keith, for the very nice introduction. First of all, good afternoon, and thanks very much for coming to our presentation. As Keith mentioned, my name is Aranya Chakrabortty. I'm an assistant professor in Electrical and Computer Engineering Department of North Carolina State University. And this demo is actually a joint work with my colleague, Dr. Yufeng from Renaissance Computing Institute, which is a part of University of North Carolina, Chapel Hill, and also my PhD student, Jianhua Zhang, who is actually sitting in the audience right now. So the basic premise or the objective of this demonstration is to show how novel methods of distributed computing implemented over software-defined networks like Genie can be a fantastic tool for guaranteeing resiliency and cybersecurity of next-generation power systems, or smart grids, as we call it these days, basically. Now, before we actually show the demo, the objective again is to use Genie and software-defined networks for guaranteeing different kinds of resiliency of a power grid against extreme events. And these extreme events can include cyber attacks as well as natural calamities like earthquakes and storms and things like that, by which physical resources are destroyed in the grid, basically. Now, before actually going into the demo, I wanted to give a little bit of perspective or context of how this problem actually arose. So I'm going to show a couple of slides to you guys. And then I'm going to hand over to Yufeng, who will actually show the demonstration using the Genie infrastructure. So basically, the topic, or the main problem formulation, started back in 2003 when the Northeast blackout happened in the United States. Many of you probably remember the 2003 blackout, and you can see the satellite pictures of New York City before and after the blackout, which created tremendous amount of economic losses. And from a power system perspective, one of the main lessons that power engineers learned from this blackout is basically the fact that traditional measurement and instrumentation technologies in power grids, which is called SCADA. SCADA is an acronym. It stands for System Control and Data Acquisition. It's a very low-resolution technology. Okay? So SCADA actually gives you 1 or 2 samples, for example, every 10 seconds. And what power engineers learned or realized from the 2003 blackout is that if you really want to keep continuous track of the health of your power grid over very small intervals of time, then such low-resolution measurements are not at all adequate, and you need to transfer to a technology which gives you much, much higher resolution visibility of the health of your power grid. Due to that, a new technology came into vogue. It almost replaced SCADA. It wouldn't be wrong to say that it almost replaced SCADA, although SCADA is still used for operations which need low-resolution measurements. But a new technology came into practice in the power industry, which is called the wide area measurement systems, or Whams, basically. And compared to SCADA, Whams gives you 30, 60, or even 120 samples in just 1 second. Okay, so it's a tremendously high-resolution measurement technology. And over here, I'm basically showing a comparison of the two measurement systems using real data that was measured in one of the substations in California. It's called Kramer. The top plot actually shows you the measurement of voltage at that substation over a span of 1.5 hours. So you can see on the x-axis, I have 5 p.m. to 6:30 p.m. So it's 1.5 hours of span. And if you just magnify that small 5-minute region, which I'm showing over there on the horizontal axis, you will see that even within that 5-minute section, there are very important oscillations and these small wiggles in the voltages which are hiding and which are completely invisible if you just use the SCADA measurements. Okay, so the low resolution of SCADA kind of prevented power system operators from catching these small information, which are very important about whether the system is going towards instability or not. Many of those information were actually not captured because of the small sampling resolution of SCADA. So just to very quickly to give you an idea of how the sensors which are measuring these high-resolution measurements, how they look like. So they are not magic boxes. They are not fancy devices. They're just simple digital relays, but with much higher sampling rate. And they are all GPS synchronized with each other because you may have some sensors in Michigan and some sensors in Seattle. And Michigan and Seattle are in 2 different time zones, but the power grid of Michigan and Seattle may be connected to each other. So you really need to make sure that you compare apples with apples and not apples with oranges. So that's why all the measurement devices are GPS synchronized. What happened over the last five years, actually, is that because of the investment grants which were given out by the US President as a part of the Recovery Act, thousands of these high-resolution sensors, also called phasor measurement units, or PMUs, thousands of these PMUs were actually installed in different parts of the North American grid, including parts of Canada and parts of Mexico, because the North American grid is connected to some parts of Canadian grid and also to the Mexican grid. So thousands of these sensors have already been installed, and as a result of which they are producing these gigantic volumes of data in different parts of the grid. And I just wanted to give a very quick glimpse of what the data resolution looks like. So in the previous slide, I showed the 1.5-hour span of SCADA measurements, and this is only for 5 seconds. Okay, so you can imagine that the amount of data that is being generated compared to the ancient technology, and now I have something like this. So you can imagine the jump in the resolution and the volume of data that is being produced all across the United States, the North American power grid right now. So then if you look at the small cartoon, which I'm showing on the right-hand side of the top panel of this slide, so then the main challenge over here is that now I have all these massive volumes of power system data, which is being produced in different parts of my grid. Now, if I want to communicate that data from the sensing locations to the control centers, where they will actually be processed, analyzed, and based on those analysis, decisions and control actuations will take place. If I want to communicate all those massive amount of data from one part of the grid to another, obviously, I need a very highly resilient, highly efficient, and highly reliable communication infrastructure, because I have to transmit this data in real time in order from the sensing locations to the control center so that decisions can be made just in time. Right? So that is basically the whole premise or the background story of how the collaboration between myself and Yufeng actually started. So I'm a power and controls engineer, and I have a power system lab, a laboratory in North Carolina State. And in that lab, we have supercomputers, or some of them which we are showing in that right-hand side picture. So those are called the real-time digital simulators, by which I can simulate very high-fidelity power system models. And I also have the actual PMUs from different vendors like Schweitzer, ABB, General Electric, and other vendors, by which I can generate these high-resolution synchrophasor data in real time within the confines of my lab. And then Yufeng actually is in charge of the ExoGeni network, which is the software-defined network component of this project. And what we did over the last 1 year is that we federated physically the power system infrastructure that I have in my lab with the ExoGeni infrastructure that he has, so that now all the synchrophasor data which I'm generating as a result of the simulations coming out of my lab, I can send that synchrophasor data through the ExoGeni network, which serves as that reliable, highly efficient communication infrastructure that I was talking about. And not just as a data transporter, the most important thing that we do in ExoGeni is that instead of analyzing these massive volumes of data in a centralized fashion, I want to process this data in a completely distributed way so that it saves my computation time, and also it bypasses the problems of single point of failure in terms of security and resiliency, basically. So, and software-defined networks like ExoGeni, for example, is a perfect platform for that, because I can create as many virtual machines as some of the talks that we have heard in this morning, for example, that we can create as many virtual machines in the ExoGeni framework as we want. And then I can send one chunk of my Synchrophasor data to one virtual machine, another chunk of my data to another virtual machine, and run local processing algorithms inside these virtual machines, and then make these virtual machines talk to each other over high-speed communication networks in ExoGeni, and try to monitor the global health of the entire power system in a distributed way. Okay? So just one last slide, which is basically what I said just now, that the main objective of this demo is basically to show that how transcending from state-of-the-art centralized monitoring and control, which is what power system operators use these days, or right now, how transcending from those traditional centralized algorithms to a completely distributed architecture using software-defined networks can guarantee more resiliency of monitoring and control of the grid against different kinds of extreme events, including cyber attacks and also physical failures due to natural calamities and things like that. So on the left-hand side, we are going to show, Yufeng is going to show two videos as a part of the demonstration. So the first video will be basically creation of a power grid infrastructure in ExoGeni in a completely centralized fashion, which is what's going on today. So we will have one virtual machine where all the PMU data, where all the Synchrophasor data from my lab will be dumped, and then we will be running a monitoring algorithm in a centralized way inside that virtual machine. And then what we will do is that we will start attacking or annihilating those communication links through which the data is coming to that centralized server. And we will show that as I start killing each of these sensors which are coming to the centralized location, I start losing the accuracy of the monitoring or the estimation that I'm trying to do. Okay, so because which is obvious that because if I keep on killing the sensors, then of course the visibility and the monitoring that I'm trying to achieve in the centralized computer is going to degrade. And then next, what we are going to do is that we are going to create an alternative distributed architecture, as I'm showing on the right-hand side of this slide. And we will show that even if the malicious hacker, for example, kills or annihilates or destroys one set of estimators, then the other remaining estimators can coordinate between themselves through the software-defined network again and try to come up with a backup leader who will take the job of the one which has been destroyed, basically. Okay? So because of the sheer redundancy that we are getting in the distributed strategy, even if one set of estimators are gone, then the remaining estimators can talk to each other. First of all, they have to detect that the previous estimator has been compromised and it cannot work anymore. So then between themselves, they have to coordinate and choose a leader. And then that leader is going to serve as the dual role of itself and in addition to the work that was being done by the estimator which has been killed. And as a result of this distributed strategy, we will show that the accuracy of the monitoring algorithm that we are trying to run, that remains uninterrupted. Okay? So that I gain much more resiliency in terms of the accuracy when I switch to distributed strategies compared to the single point of failure centralized strategy. So I'll probably, I'll just end at this point, and I'll switch to Yufeng to show the videos, which is basically, I gave the small story in this slide, and now he's going to show the actual videos, which will show the translation of those words to actual execution.
Many thanks. Before I actually show the demo,
I think. No. But his microphone needs to be on, I guess.
Oh, this is much less cooler than this. Yeah, I just want to add a few points to the testbed and the experimentation that we are going to do. So especially on the ExoGeni part. So one thing is that ExoGeni, in the terminology of everything as a service, ExoGeni particularly is a platform for infrastructure as service. So it's a federated system that can provision virtualize compute, storage, and QoS guaranteed networking resources to users, so that you can create your virtualized system, a networked system on demand. That's point one. Point two, for this particular collaboration, so as we show on the left side is more like the physical side, and on the right side is like cyber side. So this is our effort to trying to contribute to the general CPI's research agenda. So as you say, so even though in ExoGeni we provision the virtualized system, but we have a mechanism that we can connect the virtualized system to the physical system, that you can have an overall system. Oh, I have that. Okay. And the third one is we're trying to add more and more user-friendly functions. For example, for this demo, so we can demonstrate, we can emulate some simple attack scenarios or failure resilient scenarios. So in the following, I'm going to show two scenarios, demonstrate two scenarios that correspond to the two approach that Aranya just explained. And during the demo, I actually would, so the first one is a centralized case, right? So during the demo, I played two roles. So first, I'll help to provision the system. And the second, I'll be a bad guy to trying to turn it down, okay? So, okay, so now I turn the microphone to Aranya. Yeah.
So I guess over here what you're seeing is that here is the set of sensors, the 4 sensors that we have, and then this is the centralized server where all the sensors are sending their data to, right? And then we also have a visualization server over here by which you can visualize the results of the algorithm that we are trying to achieve. And let me just, it may sound a little technical, but I have to say this anyway. The specific algorithm that we are trying to monitor in this demonstration is basically estimation of, whenever there's a very large disturbance in the grid, you see all these oscillations in the power flows from one part of the grid to another. And what operators want to estimate is have a very continuous track of these oscillation patterns, basically, and how fast they are dying out, depending on which they can take their control actions and things like that. So what we are showing in the in this demo is basically how do you utilize the sensor measurements to estimate those oscillation patterns, and if any of those patterns look bad, then you have to take a control action, basically. And then the hacker is trying to confuse the operator by killing the sensor communication and spoiling the fidelity or the accuracy of those estimations. So if you go to that...
fast forward.
Yeah. Just for the interest of time, I'm just fast forwarding a little bit. 540, right?
Yeah.
So over here, you can see, in the diagram, so basically, when all of the sensor data are pure and uncorrupted, then you can see that I'm doing this estimation of the oscillation patterns, and quickly that estimation error, the error in estimation dies down to 0, which was actually shown just a couple of seconds ago. I missed it. But now what Yufeng is doing is that he's acting as the hacker, and he's deleting one of those PMUs, basically, one of those sensors, as a result of which now the operator is getting only 3 measurements instead of 4, and we will, you can keep on killing each of the other ones also. And basically, what you will see over here is that the estimation error nominally is 0 at this point, but it will jump because of that sensor being killed, as a result of which the operator is, the hacker is basically being successful in confusing the operator about the fidelity of the estimation that he's trying to do in order to gauge how the health of his power grid is. Right. See, for example, from 0 it goes to 0.2, which is a gigantic amount of error in this case, basically. And that's how the operator is, may get confused in terms of the fidelity of his estimation. So now quickly
we are running out of time, so let's run the second one.
Okay, let's show the distributed strategy. So that was the centralized strategy, which is bad. And now if I switch to a distributed version of the same sketch, so now you're seeing that each of these PMUs have their local servers, have their local PMUs, and not just one central point of failure. So even if one of the servers is gone, then the other PMUs can coordinate between each other and choose a backup server so that the estimation can keep going uninterrupted, basically. So let's show the video, maybe. Yeah, just wait a little bit, and you will see that the estimation error still remains 0 at this point instead of jumping back and forth as it was doing in the centralized case.
One more minute.
One more minute.
Yeah, one more minute.
Right. So this is the uninterrupted case, and then one of the PMUs will go away.
Yeah, now one is go away.
Right. So okay. So one of the PDCs have been killed, and you can see that the first text box, that's the backup PDC. So now that realizes that one of its teammates is down because of the attack, and as a result of which it takes the responsibility as a backup server. And you can see that the plot never, jumps back and forth as it was doing in the previous case, and the fidelity or the accuracy of the estimation of the health of the power system is still retained, and the operator doesn't get confused about what he's supposed to do. Okay. So I guess, in the interest of time, I think we'll just stop here, and I just want to show
That's what I'm trying to show you. Slides.
Yeah, I just want to show a conclusion slide, basically, just to wrap it up. So again, wide area measurement systems is a tremendously promising technology for smart grid monitoring and control, especially from the cyber-physical point of view. The main challenge over here is that you have to transmit gigantic or massive volumes of data from one part of the grid over a completely different part over wide geographical areas, as a result of which you need this very resilient cyber infrastructure. And then through this demo, what we are trying to establish is that the current state-of-the-art centralized ways of processing and communication needs to transcend to a completely distributed strategy so that you have computational savings as well as resiliency against cyber and physical attacks and damages. The project has been funded by National Science Foundation as well as the US Department of Energy, and partly by ABB Corporate Research. And we also acknowledge the support that we have got from US Ignite and ExoGeni. These are our email addresses and our homepages. All the technical papers and the reports are all available there. And if you're interested in any aspect of our work, please feel free to email us, and we'll be happy to talk more about this to you guys. Thank you very much.
Thank you very much. Thank you.